Hey, all right. So I've been pretty excited about some of the announcements today, as you might imagine from the talk. And one thing before I even start that I want to mention was that I had some conversations with the Lambda product team, and they completed four out of the 6 things that they announced today were things that I'm sure not just myself, but I had specifically asked for. And believe me, as an AWS customer, that is a huge deal when you know that they're out there doing a lot of this engineering for you. So before I even start, I just want to say thank you very much to the Lambda team. They've done some amazing work here. All right, so if you're here, thank you. What we're going to talk about today will be an expert level session. However, I'm going to get into some higher level topics at the end that I think everyone, expert and novice, will appreciate. So please don't run away if you were expecting something else. I think that this talk is going to cover some pretty unique things that none of the other Lambda talks are going to cover. There's some really awesome stuff you can do with Async Lambda, and those are all really important things to understand about architecting, and not taking anything away from there, but this is probably the only place you're going to see some of this. Specifically, I don't know if you guys caught the cascading stuff that Warner brought up in the keynote. I was very surprised to see that. That's actually a slide from this deck. So we're going to be covering that in depth. So the other last part of this that I hope you guys get out of this is the importance of interactive big data. So this isn't sort of stuff that happens behind the scenes, but how important it is to be able to get that as a very tactile feel for the end user. All right, so what was our problem? So I work for FireEye, and our mission is to find evil, and sometimes evil is in a giant mountain of data. And I'll get into just how big in a little bit. Some of this, in fact, the majority of our working data is in hot indexes, but quite a bit of it, by time period, is in cold storage on S3. I suspect this is a pretty common use case for a lot of people, and this is sort of a Lambda architecture in the more big data sense of it, not the AWS Lambda architecture. So our problem was we needed to be able to take full advantage of all of the data that we had, both hot and cold, and we needed to be able to do this in a way that's not going to hurt our user experience. So security boils down to what I call questions and answers. There's a lot of ways to look at it, but this is, over the last few years, been really important to me to define it this way. I have about 10 years of incident response experience, so I'm used to speaking at security conferences. This is kind of a new one for me to be at just a general tech conference. But I suspect that this is no different than a lot of you have to deal with. In fact, I was talking to a company yesterday, and what they were doing was very similar, but they were operating on mechanical failures. And they were trying to go back and figure out why a particular piece of machinery failed. And in a very similar way, that's what we're doing. We're trying to figure out what went wrong and backtrace. So you have two sides of the equation. You have questions and you have answers. And questions are sort of the typical security product that's going to say, hey, I've got an alert for you. And the way that we do it is through some more traditional means. We have EMR analytic output. I'll get into the specifics on the next slide. And we also have our EC2-based proprietary detection, although we may look at moving that to other forms within AWS. But primarily, that's going to be things like traditional rules, and our giant amount of intel that we have from doing all of our investigations goes into our rules so that you're getting all of your data checked against all the investigations that we've ever done. And we've done some really big investigations. If you've seen it in the newspaper, there's a very good chance that it'll say investigated by FireEye. So we have a lot of interesting things that we look for up front. But that only generates a question. So what do we do once we have that question? So that's the right-hand side. Now we have to find answers. And this has been kind of a mystery to me why this isn't the first thing people talk about in security. To me, when a product says, like if you're a SIM and you say, hey, I've got an alert for you, that's kind of like a police investigator showing up and saying, yep, this victim's definitely dead. I guess my job is done here. That's where the job starts. That's where the investigation starts. You have to find your answers. And that's the interesting thing that we had to work on. So we have two ways of doing that. We have our EC2-based index search. I've recently learned we have the largest Elasticsearch cluster on AWS. This is not easy, and it's something that we're very proud of, and it's a big part of our product. However, we can only fit so much data from a customer in a hot index. So sometimes we need to go to the cold stuff, and that requires Lambda. So what are we doing specifically? So in EMR, we have our traditional big data kinds of things. So we're doing our clustering, we're doing things like linear regression. One of the interesting things that we do that I find easiest to explain to the novice in big data is geographic timeline, and we call it geofeasibility. So if we have 2 logins from 2 different cities at the same time on a mobile device, that seems pretty improbable, and we flag that as an alert. And in this context, that's a question. The question is, why did this person log in from 2 different places at the same time? So that triggers our investigation. And that's where Lambda can help us out here. Again, we have, the majority of work is on that hot index, but sometimes you got to go much farther back in time. And for that, you might need to do some basic group by style reporting, and those might be multi-column things. You might have to do some more in-depth aggregation. The visualizations help. We'll show that in a second. And you might need to do some statistics on there as well. And this is the part when I was working with Lambda that really surprised me. I assumed that because there wasn't much code involved in what I was working on, that this wasn't going to be very powerful. And what I found was just using even some of the Node libraries out there for things like k-means and linear regression and deep neural networks. There's a fair amount of libraries out there for doing some serious data science, and when you put it on Lambda, it's actually pretty fast. And I find it to be as or easier to use than your traditional Spark-based data. So when you're doing big data, a lot of the times a bar chart and a table is the best way to show it. But I feel obligated to show some of the cool things. Everyone here, I'm sure, knows D3, loves D3. And I do want to point out how important it is to sometimes show you've got outliers there, and these form questions of themselves. So sometimes you get this loop where you have a question comes in the form of alert, and you go find an answer, and then that forms more questions. And so you keep going and going and going. And this becomes a really important workflow to understand later because it explains why batch processing doesn't help us very much. So everybody talks about big data, right? There's a million really funny sites out there that spoof kind of some of the work that we do, right? And because some of it's really ridiculous. We use math to do magic, right? That happens a lot. Sometimes some of it's deserved, some of it isn't. So here's how big our big is, just for level setting. And I'm sure there's much bigger, and I'm sure there's much smaller. I've seen many cases where people call a few million records big data, and like, okay, that's cute. And then there's places like Netflix will just laugh at this. I mean, I'm sure they have hundreds, maybe thousands of petabytes, right? So that's a whole different ballgame. But this is to frame your context for the kinds of things I'm describing. So you're saying like, okay, well that maybe works in your use case, but mine looks like this. So this should sort of help you. So we work with security event data. These are the mountains of data points that we're going through. And each event is about, on average, 3,000 bytes. And again, this is for an average customer. And this is what I want to point out. This is not the entirety of our data. This is one customer. And I'm not at liberty to say how many customers it is, but it's enough that this becomes very important to be able to do right and do well at scale. So we have 3,000 bytes, and an average customer has about 20,000 of these events coming in per second. So that's 60 meg, about 5 terabytes a day. That's like, okay, that's a lot of data, right? But that's one day. So even searching 1 week, you're talking 12 billion events and 35 terabytes. Now, if you got that on an index, no problem, right? We can go through that in under a second for most searches on our hot index. And that's nothing to shake a stick at. That's very important. However, what happens when that rolls to cold storage? What are you going to do with 35 terabytes? That's a lot to get through when you don't have an index. So how long would that take? It's like, well, all right, we'll spin up grep, right? We'll just grep it. So this is how long it would take. It would take you 4 days to grep 7 days worth of data. This is clearly not going to work for us. So it's like, okay, well, we'll throw some stuff at it. Maybe we'll auto-scale, maybe we'll do EMR. So it's like, okay, what is it going to take? Well, 10, you're looking at 6 hours. And this is where that loop that I was talking about is so important, because when you're doing an investigation, you don't know that what you're going to ask is going to be the right answer. You might have to ask a number of questions. So the longer you have to wait to find the answer for what you just asked is going to lengthen and lengthen and lengthen your investigation, when often time is of the essence. So if you're waiting 6 hours during your investigation, that's not going to be very helpful. I mean, that's an overnight job, right? So can you imagine doing an investigation, say, well, I'd be really interested to know what this host did. I'll check on it tomorrow. I mean, that's tough. That's tough. So, okay, we'll throw 100 processes at it. Well, now it's an hour. Okay, now we're talking a long lunch, right? We're still doing pretty well here. But let's think about that. 100, well, let's see, biggest box you can get is what, 40 vCPUs? So you're talking 2.5 there. So that's not nothing, but it's pretty doable. But still, you're waiting an hour for that, and that's significant. So okay, let's get this down to something where you can ask multiple questions without getting up from your desk. Well, now we need 1,000 of these. So now we're down to 5 minutes. This is somewhat tenable. Still not awesome, but you can actually use this in an investigation at that point. And if you really want to, you can do 10,000, and now we're cooking. Now you've got a few seconds. Now you're sipping your coffee for a second while you're watching results come in. So that's pretty important, right? That's directly ties to the length of your investigation. So let me pose that again. How are you going to do an auto-scaling at 1,000 processes? You can do it, right? I mean, the answer is always yes. Yes, we can do that. But it's going to be kind of tricky, and it's going to be a little bit painful. And it's not something you're used to invoking by a user from a web interface. That's kind of a shoehorn at that point, right? There's not a lot of times where you have your customer invoking EMR jobs that are expected to finish within a couple of minutes. It's not saying you can't do it or that you aren't, but I'm saying there is a better way. So that's where Lambda comes in. So what if you could spin up 10,000 CPUs in 100 milliseconds? We've never been able to do this before. And I'll get to more what this means at the end of the talk and some of the higher level stuff, but this is a big deal. So you're able to do the standard map reduce pattern without any of the hassle of the EMR stuff. And it's not that EMR is bad. It gives you the time windowing in Spark, and there's a lot of reasons why you need that. On the other hand, there's a lot of use cases for analytics that don't require the full spectrum that Spark gives you, or that you can roll your own. And when you have something that can spin up this quickly, there's a very nice trade-off that happens. And primarily, you get much, much simpler code. And this is what I loved about it, because I am an average programmer at best, and I guarantee you, if I can do this, anybody can do this. And that was kind of what was interesting to me, is suddenly I could ask really, really big questions, and they would all just come right to me. And this had never been quite so easy before. I didn't have to go and have an EMR cluster provisioned. I didn't have to set up all this stuff. I didn't have to take the weeks of prep to set this all up. I said, hey, this worked on this one file. Let's try it on all of them. And then about 5 minutes later, I had my result. And that's when this started to get really, really cool. So this is the Cascade process. And I noticed they didn't change a whole lot from the keynote this morning. And I kind of, if I had known about it, I would have offered to change a couple of things on it. But this is basically the pattern. I'll go in depth on each one of these in just a second. The thing I want to point out here is at the bottom. This is straight from my blog post I did for the AWS Big Data blog. And what this means to you is that the source code is available there on GitHub for you guys to go check out, literally check out. And you can run any of this stuff. So I did a word counting function, the hello world of big data. And I didn't do any of our normal stuff on there. But that gives you that sort of bootstrap to say, like, oh, I can do this too. So let's go through component by component. I tried to simplify this a significant amount just to show where the mapping and reducing comes from, if you want to use the classic terms, right? So the initial request comes in on a very basic web app. Now, when I first started on this, API Gateway was not available. So I did this all on Node with Express, just kind of the standard basic setup for Node. But you could use API Gateway, which would remove all of the servers entirely from this, which becomes even more interesting. And again, I'll talk about that in a little bit. But that doesn't really matter in this setup. The idea is that you have a Joe Schmo customer and user is going to be invoking all of this. And they're going to be expecting a response back immediately, not in a few minutes, just right away. They want to know what they're getting. So the basic web app handles that and then streams the results back. And we'll get more into the streaming towards the end. The Cascade function, this is going to invoke a bunch of child workers. So this is where you spread out. This is the map part, right? And this part can be made recursive. So if you asked for 100,000 lambdas to be provisioned, I mean, that would be a pretty tall order. 10,000 was not a problem. 100,000, who knows, depending on your region, what you'll get. But theoretically, you could ask for that. And you're going to be able to do that if you just have another layer of cascading. So the answer is going to be always yes on this. It just depends how many cascade layers you want. And the important thing here is it's going to do two things. It's going to aggregate the results, which means your initial requester, e.g. the web app, Node, this poor little single-threaded node, is going to not be inundated with 1,000 responses. It's going to be inundated with maybe 100 responses or even fewer, depending on how you have your cascading. So there's your reduction, right? And then, of course, your worker function. This is the cool part. You just write that as your basic little Lambda function, and if it works on one file, it works on all files. And that's really the fun part of developing this, is that that thing is going to grow to be giant when it gets invoked by the Cascade function. And I'll talk more about the DevOps part of that in a little bit. So because it's expert level, we're going to do just a teeny bit of code. I don't expect you to really care about the code itself here. I'm going to go over just a few of the finer points on Node, and why Node is kind of a helpful way to do this, although I was really excited, and again, I asked for the Python thing, so I like both Node and Python, and I think they both have their strengths. So one of the strengths of Node is that it's, streaming is kind of one of the things it does very, very well. So the event stream library has been with it for a long time. And the key part about streaming is that you can be working on any large data set, but you're only ever operating on chunks of it. So your RAM usage is always going to be very small, even though you're working on something very large, right? So the idea is you're not like downloading a whole file right here and then churning through the whole file and then operating on the next step like a waterfall. You're working on just a little bit of window of the data the whole time. And that's critical because you want to be returning responses to the user during this time. So let's walk through this. So the initial thing is the list stream. This is a really, really dumb Node module that goes out and says, hey, I'm looking for all the keys under this prefix in S3. Mike Deck, an AWS solutions expert, I believe that's his title, has another talk out there, hopefully you got to it, in which he showed how to index S3 and put it out on DynamoDB so you have a nice directory, which would make this much better. In our current implementation, we're actually limited by the speed at which we can list keys off of S3. That's the overall bottleneck. And of course, there's lots of ways we can deal with that in the future, in addition to just having a normal directory. In any case, it all starts out with getting a stream of keys that we want to search, right? So we're getting a queue of our work. And that's going into the actual Lambda stream thing that's going to be invoking the Cascade workers. And here you can tell it how many workers to invoke at maximum, and that's important because you want to stay under your provision threshold, which is 100 by default. You have to request a limit raise to go up to the 1,000 or 10,000. So when you pipe it all together, you have a list of keys coming into Lambda, and then we have this end equals false thing here. And this tripped me up for several days. This one is a little bit annoying, and I'll get to that in a second. The results then are sent over just a tiny little 5-line thing that does a server sent stream. That's the HTML5 server sent framework. That's very similar to a WebSocket, but with a little bit less hassle, and it's just unidirectional back to the user. For this, that's all I needed. I didn't need any bidirectional stuff. It's very, very easy to use, and that was my choice because it fit the bill, and it was seriously like 10 lines, the whole thing. And then it goes right into the HTTP response. So the key here is that the web user is seeing a new line separated feed in real time as that whole pipeline is operating. So there may be hundreds of thousands of S3 keys that we're going to search through. And if we can get the first couple of them done, those results are streamed back to the user in under a second, even though the whole job won't be done for maybe a minute or two. And that's great, because then the user gets something to look at right away. And for instance, if they see that they made a typo, they can cancel the search and enter what they really wanted instead of finding out at the end of a giant batch that it was all wrong. And they can also, more importantly, get approximated results as things are coming back through. So the batched async execution, this is the tricky part. So the pipeline stuff works great in Node. The problem and the trick is with this end false, because so we have all these keys coming through, and they're going to Lambda, and then it's doing its thing. These Lambdas are out there parallel invoking, and they're returning the results to the end user. But that tail, that caboose on those, that's going to be a problem. It's going to get trimmed off, because as soon as that list stream says, I sent all the keys, those things that are asynchronously out there working in Lambda land, those are going to get cut off because the pipeline's done. So you have to stick an end equals false on there to say, I will tell you when we're done. And that's a very simple state tracking to say, hey, did all the Lambdas come home yet? OK, great. Then we can issue issue end, and then it'll close the pipeline correctly. So that was a little bit tricky. And that was the only thing that was tripping me up in the event stream stuff. Otherwise, it was a very good pattern to use. The nice thing about the pipeline is, as I showed, you can tell it the maximum you want to be going at one time, and that'll keep you under your provision limit, so you're not dealing with like a retry avalanche, where you're sending a whole bunch of Lambdas and it says, hey, you already sent 100, you're provisioned for 100, these are all failing. You don't want those to back up. All right, so into the Cascade function. This is the middle. So this code is ridiculously simple. I'm just bringing it up to show, this is a for loop that creates a batch of batches, right? But that's all we're doing here. We're taking a giant list of keys that goes to a Cascade function, and we're going to break that down into smaller batches, and each one of those small batches is going to be given out to a worker. And we're going to give them to the workers in parallel. So we're not going to wait, we're not going to do it in serial where we're waiting for one to come back and we'll do another, right? We're going to do them all at the same time. So the entire execution is only as slow as the slowest worker. And generally speaking, when you have this much data, it all pretty much averages out. There aren't too many outliers, but it doesn't really matter if there are. Generally speaking, you're not going to have a problem here. All right. So as I mentioned before, the key thing here is that we have a point to collect these results. And when you're tuning this, the thing to understand is this is what you have to tune for your data set. Based on your workload, this has got to stay under the provisioned amount of memory that you're allocating. So you have to kind of understand what's going on there, do some error checking, and most of the time, I've not run into problems once you get your basic pattern going. And your files, you're going to know ahead of time from S3 how big your files are, so that's usually enough of a check. In fact, you can split your batches up by size instead of number if you want to do it that way. And what I have found is that you can go full bore 100 to 1 for a cascade to worker ratio, and you can't actually go higher than that. What I have found is that the maximum number of API calls you can make is about 100 per second, and that's purely limited in Node by Node's HTTP library, how fast it can go. And that's, because behind the scenes, you're just making HTTP requests, so that's actually your limiting factor there is how many HTTP requests can I make at once? And so now you see the importance of being able to do a cascade is not just to aggregate the workload, but it's also to distribute the work of invoking the functions themselves. If you tried to, just at that original Node.js process, invoke 1,000 lambdas at once from one spot, not only would you have too many results coming back to handle from one, you wouldn't be able to invoke more than 100 at a time. So you're going to have to, it's going to be at least 10 seconds before all of them are even invoked. All right, so the worker function, again, is from the blog. This is almost hello world-ish, but basically we're going to take S3 and we're going to stream the files off of S3. And this is really critical that we're not downloading the whole file because remember, we're being paid per 100 milliseconds. So we do not want to be waiting around at any point. We need to be saturating the CPU all the time or we're paying too much. And that's really your tuning factor is at any time did I have extra CPU, that's a bad sign. So I want to make sure that I'm saturating that CPU. This is great because you're not waiting for the whole file. The second that the head of the file arrives, you get to start working. So you're not waiting for the tail, you just get the head. And that's usually, I was seeing 15 to 20 milliseconds from S3 to Lambda. I mean, we're talking really, really fast, especially if you've accessed that file recently and there's a little bit of caching going on. You have to ask the S3 team how that works, but I've seen some ridiculously fast downloads, and that's great. So the other thing that you want to do is do this all concurrently, and I'll get to that in a second. So the basics lineup here, though, we have our S3. It's you just do create read stream. You're going to unzip it in our case, and then we'll split it on new lines, and now we're operating on actual events. All right, so these are some of the main tips and tricks here. So we talked about downloading concurrently. This is a really interesting one. You want to make sure that you are using, for a workload like this, as much memory as you can throw at it. If any of you used Lambda before, you know that they allocate vCPU time in accordance with the RAM. So you're not necessarily going to use much of this memory at all, but you're asking for basically how much percentage of one CPU time are you going to use. So unless you want to be waiting around for no reason, if you're going to saturate that CPU, ask for the whole thing. So let me give you an example. Let's say you did 250 meg for your Lambda size. You're going to run at 100%, and it's going to take 4 times as long as running 100% at 1 gig, right? So there's no reason, if you can saturate the CPU, to ever go less than full throttle. In our experience, downloading 2 to 3 meg S3 keys is, you can do 5, 10, 15, somewhere in that range works pretty well. Again, whatever you can do to make sure that you're saturating the CPU. And this one's kind of interesting. So our team did some research on compression, and generally speaking, zlib is always your best bet for the size to decompression speed trade-off. And in this case, since you're paying for storage on S3, that's usually where you want to be, is in that sweet spot. However, if you find you're in a use case where you're doing a lot more access than you are storage, like maybe you're not storing things for very long, LZ4 with high compression might be worth your time. And the reason is, while the compression speed is about the same and the files are slightly larger, we're talking 25, maybe 40% larger, which is not good for storage, you can get really fast decompress. And that means a lot less Lambda CPU being used. So that might be worth your time to look at. Again, if you're not going to access these files very often, though, you're probably going to be paying too much in S3 storage to outweigh the CPU cost. But that's something to look at for your basic use case. And the last thing, and this should be obvious to everyone, but it's really important that in this cascade structure that your errors are getting boiled all the way up. So even the weird ones all the way down need to be trickled all the way up so that the user knows. In our case, it's very important. If there is an error anywhere along the way, that taints our result. Because if you say, have we ever seen this bad guy in this giant mountain of data and there's an error, we want to know two things. Okay, yes, we want to know if there's an error because that might invalidate our result and we can't be sure about it. But we also, if this is a big job, we want to know where that error was because we don't want to have to run the whole batch again. We want to only have to run that sliver where the error was. So really full error reporting is really important here. Now the last thing I want, or not the last thing, but the next thing I want to talk about is the fact that you don't have to pull this off of S3. So everything I've shown so far has been S3 oriented because that's how we use it. But it doesn't have to be that way. These are just computers. They're just computers running for a short amount of time and doing whatever you're telling them to do. And as we learned today, they can be running in a VPC. So you can go out to the internet, you can do Dynamo, you can do RDS, you can do Kinesis, and very interestingly, you can hit your own APIs. Maybe you've got your own CloudFront or your own EC2 instances running your own proprietary stuff. There's no reason that these guys can't come and hit that and then use the data there. It doesn't have to be S3. So anything that you need extra CPU for, you can grab that in 100 milliseconds. So as a little example, and this code was not worth releasing, but I thought it was an interesting test case. So one day I thought, I want to know what what do my followers feel about something? And I thought, I thought of this because I came across the sentiment analysis engine, and I thought, that's kind of cool, natural language processing. That's always a fun thing to look at. And for us, it's not really super important. It's more of a toy, but for a lot of places, it's bread and butter. So there's a lot of good libraries out there. And I thought, well, wouldn't it be interesting to see if you give it any username on Twitter, go dump all their followers using the Twitter API, and then we'll invoke a Lambda to operate to run the sentiment analysis on each one. So the inputs are username and a term to look for, and we're gonna search Twitter for that username and this term, and we're gonna analyze it, the sentiment in Lambda for positive, negative, and neutral, and hopefully this animation shows up. Looks like it is. There we go. So this is pretty cool. I mean, it's fairly useless, but it's important to show that we're getting data back to the user right away in a very visceral way. And I'm just looping this, but that was kind of I ran through a bunch of these, and this was probably the best. So let's talk about the importance of streaming results. And this is really the difference between doing your standard big data EMR style batches versus something like Lambda. And that is progressive results. So in UX time, if you see a spinner for 30 seconds, your app is broken. That thing's probably never coming back. If it is, that's a terrible UX, right? 30 seconds is ridiculous. I mean, 3 seconds is ridiculous most of the time. When people are used to doing search results, they may tolerate 2, 3, 4, 5 seconds. But 30 seconds, that's a long time. So even in our smaller Lambda searches, we still need something to come back right away. And we don't want a dumb progress bar, because a progress bar says go do something else. That's not what we want. We want our users to be looking at the app, and we might actually be able to tell them something very helpful right now. So we want to go beyond a progress bar. We want to show the results that we have so far, because they may already be very interesting. Case in point, you're looking for a bad guy. You put in, let's say it's a bad IP address, and something pops up right away, and you start getting a bazillion results, and you realize, like, okay, either this is very bad or I typoed this. So that's something that you can answer within 3 seconds, and then you know, okay, well, we either continue this and let it run and see like the actual final number, because maybe we need like an exact count, and that's really important for the investigation, or we know we're not interested in this at all, and we don't need to let the whole thing finish. So that's not a brand new idea, but I think it's pretty new from a big data standpoint. And I think it's really important that you're not just getting a stream of text back, that you actually have graphics that are showing what's going on. So this is a really, really rough prototype I had a while back. And this is what it looks like when the things come back. Right, so you guys have probably all seen this in some other products. But the fact that this is coming across something like 35 terabytes is a little bit more interesting. And one thing that's kind of cool about it is you can see right away that, okay, the first thing you know is we had results in all of these time periods, right? There was no time period that we didn't have a result for. That's an immediate assertion that we can make. And if we were going to just have a spinning progress bar, you would never know that. The second thing is that it's kind of like a fractal where things get less and less blurry the more you have. And so you can see that there are spikes that show up, and they get more and more defined as time goes on. But there's still value in the immediate spikes. And on the left, you can see that we have, well, maybe you can't, but there's distinct values in field counts that grow as the search runs. And so at the final end, and you see the most granular search results and says, hey, we're all done. All right, so that's most of the super technical stuff, but I really wanted to spend some time in this talk to really emphasize how important Lambda is. And I think Werner stole a little bit of my thunder in the keynote today, because what he said was so true, that we've never had this power before. This is the first time we've ever been able to spin up this much compute this quickly, this easily. There's nothing like it. And I don't know that everyone has really wrapped their head around the fact that they don't need to do a lot of work to get a lot of CPU really fast. But that's only where it starts. So there's a bunch of other talks talking about serverless architecture, and these are huge. These are such a big deal. Because let's think about what it means if we didn't have servers. We don't have operating systems, and we don't have networking. What are we left working on? Just the stuff that matters to our customers. And that's what's so powerful to me, is that the only code that I'm writing is code that is directly benefiting the customer. There's no overhead code. There's no infrastructure code. I don't care how or where it's executing. It's going to get done, and it's going to be just the bare minimum that I wrote. So we can focus on our core competencies. The other nice part is on the DevOps side. So when you're writing the code, if it works once, it always works. Unit testing is really, really easy. Somebody has a Node project out there. I saw it on Twitter, and it will emulate a Lambda run just from a unit testing perspective. So that's available if you want to look at using that for something that's either not on the internet or something like that, if you need to do air-gapped unit tests. But honestly, when you're only doing one, I mean, we're talking hundredths of 1 cent worth of execution. You can afford to have like Jenkins or Travis or something actually spin up a real Lambda. In that case, it's gonna cause any sort of significant cost. So you can actually run the real Lambda and see it go. And this kind of reminds me of containers. So you have the same situation where the great thing about Docker is that, and there's that old, I think it was actually an Onion article where they said, dev guy doesn't understand why ops guy doesn't care it worked locally, right? And so I was like, it worked for me. I don't know why it's not working in production. And so Docker helps a lot with that, right? Because you say, well, I have this exact environment. I'm going to put it out here. I mean, we go beyond that with Lambda. So Lambda says it's the exact same code running in the exact same environment, and you don't have to worry about what the environment looks like or what the networking looks like or any of that stuff. We always know where that code is. And that code can be updated without any patching. When you're executing a Lambda, it's the same code that you said, update Lambda function, and it's right up here. And whenever a Lambda executes, they go and they grab it. That's the exact opposite of something like Ansible or Puppet, where you're pushing down all your patches to everything and hoping that it gets to everything. This is a situation where you update it once, and you're guaranteed that every time that runs from then on, it's going to be running the exact code that you uploaded. All right, so I'm coming up to the end here. It occurred to me that when I was talking about, well, what do we need servers for? In the last job that I worked at, I was at a data center, and we had a couple of really giant mainframes and some people twice my age that operated them. And their stuff pretty much never broke, and it was really interesting. It didn't do anything that I thought was cool. I mean, it's just, finance stuff or whatever, nothing super flashy like D3, right? But it was important, and it always worked. And they didn't have to care about networking. They made some LPAR stuff. But generally speaking, they didn't care how their code was getting executed. They just wrote it. Now, why isn't that super prevalent in the 80s and 90s? Well, people had graphical user interfaces, and that's kind of anti-mainframe because they didn't have any bandwidth back then, right? So you're on your 2400 baud modem, if you're lucky back then, you're not going to have any kind of significant graphical experience that way. So now, fast forward, we have both, right? We have the ability, we have the cloud, we have these giant computers that you don't see on a daily basis, and we have broadband that's actually going to bring down all that rich content as quickly as it can. And so we have the centralized compute, and we have everything we need to from there. And I think it's important to just kind of look back and say, I mean, so often we think, oh, everything's brand new, but, you know, we've got a lot of repetition, and there's a lot of lessons that we can learn from back then. On the other hand, things are much improved, and that now it's much easier to get things deployed. And there's a couple of related sessions. I think this one ended up being scheduled alongside, so that was kind of unfortunate, but I do encourage you to check that out. When I submit the slides, they didn't have the schedule down. All right, so please remember to complete your evaluations, and are there any questions?